Doctor, we can't hear you.
Can you hear me now?
Yes,
Yes,
yes.
now we can.
Okay. So, once again, we will discuss the important concept of general mechanics, which is work and energy. Energy is so important physical value that it is connected different fields of physics. It's present in mostly in every um, field, in every branch of physics. For example, it's present in mechanics, in thermodynamics, in electricity, in nuclear physics. So all the fields include the term energy. And initially it is defined in mechanics, and then in electricity the definition can be different, but it is related to the definition from mechanics. And in mechanics we should start with the value which is called work done by force. So if the force and displacement of a material object has the same direction, then the work is defined as a product. W work is a product of force S and displacement S. If the direction of force and displacement do not coincide, then we should add a cosine alpha, where alpha is the angle between F and S. The same equation can be written in the form of scalar product of vectors. So F multiplied on S in scalar form. Well, again, this is important concept. Let us see why. Because if we consider a point particle moving in space, then the work done by all the forces on this particle is equal to change in kinetic energy of the particle. So from Newton's second law, we can show that work equals to m divided by 2 and changes in squares of velocity. So if you are interested in why we need to divide m by 2, which goes from integration. If you know the integration operation, you can know that if we integrate, for example, x dx, we obtain x squared divided by 2. The same takes place in case of integration of velocity on actually integration of Newton's second law with the trajectory in space. Well, and uh, this is equation which is general, which can be applied to any kind of force, but there is some class of forces which are called conservative, which can be represented as change of some function of um, spatial coordinates of the particle, of the rigid body, for example. So the work done by this force does not depend on trajectory. It depends only on initial and final position. Only in this case we can define a function which is called potential energy, and this function determines the work of such forces. Uh, there are many conservative forces in nature. most widely known in our everyday life are the force of gravity and the force of electrostatic interaction, the force of interaction between charge and electric field. In case of gravity, on the surface of Earth, we can easily write this potential energy as mgh, where h is height, m is mass, and g is standard gravity. But it is not necessary always to say that delta E is equal to mg delta H. There are many different configurations of field which can be considered with this equation. For example, electric fields produced by point particle, by point charge is completely different from MGH, and anyway it is potential field, and the force of electrostatic interaction is conservative, and there are many different objects which can create electric fields, so we can consider very different configurations of fields. But every time the work does not depend on trajectory, it depends only final and initial point. In this case, in case of conservative forces, we can see that if we combine equation 3 and 4, we get that minus delta EP equals delta EK, and it means that sum of these two changes of energy is equal 0. That means energy, which is the sum of EK and EP, is constant. So this is very important law of energy conservation, and it is very important that it is valid if the forces, all the forces, are conservative. For example, we have some non-conservative forces, which can be a force of friction, for example, a drag force in fluid. They are not conservative, that's why energy conservation law is not valid in this case. But it is found from other fields of physics that actually energy does not disappear. In case of friction and, for example, drag force in fluid, the energy just changed its form. It came from macroscopic mechanics form to microscopic, to the energy of motion of molecules. And the total energy, if we include the energy of molecules in our total energy, then the total energy still remains constant, even in case of friction present and some other non-conservative forces. And for example, if we consider chemical reactions, then mechanical energy is not conserved. But if we include energy of chemical reactions into total energy, then it is again conserved. So it is one of the most fundamental laws in physics, the law of energy conservation. And here are the few words about energy. I remind you that my presentations can be found in some folder. I'll give you the file with the links to this folder again at the end of the lecture, because more people will present at that time. And the links are the same. I was giving them to you last week, for example. And in the folder, you can find not only lectures, you can find a textbook and some other files, and files with links to videos for the lectures, for example. Well, and there is some text to be read for you in my presentations that I sometimes omit during my speech. So here are a few words about energy. So let us go to the next slide. Yeah, here is the beginning of mechanics of fluid. We have discussed mechanics of point particle and solid body in 3 previous lectures. Actually, we have included not only those 2 models, not only point particle and solid body, but we also have considered waves in the medium, which is actually not just a mechanics, it's a sort of mechanics of continuous medium. And another sort of continuous medium is fluid. And fluid is a gas or liquid that assumes the shape of the container in which it is placed. And it is interesting that there is no analog of word fluid in Russian. In Russian, we have the word for gas, the word for liquid, and there is a field mechanics of fluid is called mostly hydrodynamics, mechanics of liquids in Russian. Well, and let us discuss the main equations of this branch of physics. We will discuss some simple task. The task is to find the variation of pressure, velocity, and maybe heat in case of a tube through which the liquid is flowing. So let us start with finding the mass which passes through the some given cross section of the tube in the time delta t. For example, if the cross section equals A1, then the volume of liquid which passes through time delta t equals to the volume of this cylinder with the base A1 and height or length equal to V1 delta t, where V1 is velocity of the liquid in this part of tube. So we can write that delta V equals to A delta X equals to AV delta T. And if we want to find mass, we should multiply this on density rho. So delta M equals rho AV delta T. Let me check what we have in the chat. Okay. Now we have this equation for delta M, and of course mass is conserved. We cannot have any process when the mass disappears or appears from nothing. That's why when the liquid flows through the tube, delta M is equal at every part of the tube. And this ratio allows us to define the new physical quantity, which is volume flow rate, which is defined as volume passing a given cross-section in time delta t, and is a ratio of this volume to time delta t. So Q equals delta V by delta t. And from the equation 6, we can see that this volume delta V equals to A V delta t. So if we divide it by delta t, we find that Q equals AV. And since since rho is the same, delta M is the same, Q also should be the same in every part of the tube. That's why if Q is constant, we obtain that AV remains constant at every part. So for example, here we have smaller a, then we have larger V. And if A is bigger, then V is smaller. Well, this is known as continuity equation, a very important equation of hydrodynamics, of mechanics of fluid. It is valid every time when we discuss uncompressible liquid, uncompressible fluid. In most cases, it is applicable not only to liquids, but in gases also. But in liquids, we can say it is valid almost every time. Well, we have discussed before that the kinetic energy is changed if we have a force acting on the solid body. The same is true for fluids also. There is no big difference in this way between fluids and solid objects. That's why we can say that change in kinetic energy equals to work done by all forces. In this case, we can discuss two types of forces. One type of forces is potential force of gravity, and its work is equal to EP mgh. So we can include this potential energy into the total energy. Then we can say that external force changes not only kinetic energy, but it changes total energy of the liquid. And this gives us to the equation 8. So in equation 8, we can see that change in total energy of liquid is due to the work done by external force. External in this case means the force which makes the liquid to flow. And this is a force of pressure. So we can find its work directly by multiplying force on distance or force on displacement. Force can be found by multiplying P on A. Because of the definition of P, P is the ratio of force to area. So we know the force in this place, we know the force in that place, and we are able to find the work done by these forces. But before we do this, let's just consider other terms in equation 8. We'll start with the change in kinetic energy. If we consider motion of liquid from this part of tube to that part of tube, then velocity is changed, and change in kinetic energy is found by the change of velocities v2 and v1. They both should be squared before finding difference. And we have this form if we remember that delta M, the mass of this part of liquid, is equal to rho Q delta T. We get this equation 9. Now let us consider the change in potential energy, which is due to the change of H, which is denoted as Y in this equation. So if y increases, the potential energy increases, and its change can be written in form 10. Again, m is represented as rho q delta t. And now we should calculate the external work done by pressure. As I told, the F can be found as a product of pressure on cross-section area, and delta X, the change in the displacement of liquid, can be found as V multiplied on delta T. So we have P1 A1 V1 on delta T minus P2 IA2 V2, because we should subtract work done by the force in this region. We are going to find the total work, and in this region pressure makes a positive work if it is coincide with the its direction, the direction of force produced by pressure coincide with velocity v. And in this case, the pressure is done negative work, so it's external pressure goes from this cross section and it is directed opposite to v. That's why we have a minus sign here, and we have changes of pressure P1 minus P2 on in equation 11. If we now combine all the equations, so here we have work done by external force. Here is the change of kinetic energy, and this one is change of potential energy. We have this equation 12. In this equation, we can see that we always have the same Q delta T. So Q delta T is volume of liquid, and this volume remains the same because liquid is uncompressed. So we can cancel Q delta T in all the terms. This gives us equation 13. I have changed the well, some terms are changed their position, and that's why we have a combination of P rho V1 squared by 2 and rho Gy 1. So this combination for the first point, and the same combination but with indexes 2 in for P, V, and Y is on the right hand side of equation, which means this combination P rho V squared by 2 rho Gy remains constant during the motion, and this is known as Bernoulli's equation. Now I'd like to show you some video, and I'd like to show you my new file with some links for lectures. So let us try to use
Bernoulli's
the
principle.
first link from this file.
The flow of a fluid is streamlined if every particle of the fluid flows exactly the path of its preceding particle and has the same velocity as that of its preceding particle. Consider a fluid moves through a tube of area of cross-section A1 and A2 respectively. The volume of water entering A1 per second and the volume of water leaving A2 per second. Therefore, mass of liquid entering per second at A1 and mass of liquid leaving per second at A2. Assuming there is no loss of fluid in tube, that each for ideal fluid. Therefore, or AV equals constant. This is the equation of continuity. When fluid flowing through a section of pipe with one end having a smaller cross-sectional area than the pipe at the other end, the velocity of the fluid in the constricted end must be greater than the velocity at the larger end. Bernoulli's equation applies conservation of energy to formalize this observation. Consider a tube AB of varying cross-section A1 and A2 and at different heights H1 and H2. Liquid is flowing from A to B. P1 is greater than P2. Here, A1 is greater than A2. So, V1 is less than V2. The force on the liquid at A and at B. Now, the work done per second on the liquid at section A and at section B. V1 equals V2 equals V. Equation of continuity. Net work done equals P1V minus P2V. The net work done per second is equals increases the potential energy and kinetic energy per second from A to B. According to law of conservation of energy,
So, well, let me go back to my file. So I hope you were able to hear the sound during the demonstration of video. Can you? Please.
Yes, doctor.
Okay. So we'll see some other videos, and the links to all those videos can be found in a file which I'm going to send you later, because I'm afraid that if I send it now, those who will connect later will be unable to get it. So at the end of the lecture, I will send you files with links, and once again the link to the folder with lecture, so you will be able to have all necessary materials. Well, now let us consider how this Bernoulli's law is applied in medicine. We have discussed some general concepts without application, but now let us consider some applications. And first application we'll be discussing of, wait a second, I'll try to mute the microphone. I don't know who's it. Maybe this one. Well, I think it's okay. Now, if we consider a aneurysm, which is a weakened wall of a blood vessel, which leads to increase of cross-section area of the blood vessel. On the first view, one could think the larger cross-section, the smaller velocity, the smaller pressure, so it is easy for blood to pass this part of the vessel. But actually, from the Bernoulli's law, we can see that if velocity decreases, I'm sorry, then P increases, because if we have the same Y and this term just not important, rho G8, then we have two terms, P and rho V squared by 2. And the larger V, the smaller P, and vice versa, the smaller V, the larger P. That's why the wider part of vessel, where the speed of blood is smaller, will have the larger pressure. And instead of easy flow, the pressure will be higher, and the pressure will continue to increase the damage of the vessel wall. That's why it is very dangerous disease when the unibrism appears. It continues to increase, it continues to destroy the vessel, because blood pressure in the wide part of vessel is not smaller than in a narrow part. It is actually larger. And this estimation are valid for ideal liquid. For example, it is shown here, it is written here that if radius of the aneurysm is n factor greater than the radius of the blood vessel, then area will be n factor, n square factor larger, and that's why velocity will be smaller by the same factor. It is correct, but estimation of pressure from Bernoulli's law is not absolutely accurate, because it is valid only for ideal liquid with no viscosity, with no inner friction. Anyway, even if we take viscosity into account, the pressure in a wider area will be larger than in narrow area. Well, another example is the artery with a partial blockage. For example, this is deposit which blocks partially the vessel cross-section. So the vessel cross-section becomes smaller, and one can assume the smaller cross-section, the larger pressure. But from the Bernoulli's principle, it states that the smaller cross-section, the larger velocity, and the smaller pressure. And the smaller pressure means that the wall on the other side will not be affected by the pressure, and outer pressure can decrease the cross-section even more. So we have the situation which is dangerous, because outer pressure can completely block the narrow part. Of course, if it blocks, then there is no velocity, and then there is no blood flow, then it means the pressure increases again, and we'll have some pulse of blood in such a narrow vessel. But even if it doesn't block completely, it makes the channel even narrower than it was. So the common impression that the narrow channel should have larger pressure is not correct. which has smaller pressure. That's why it is dangerous, and it becomes even more narrow due to the Bernoulli's principle. So this is application of Bernoulli's principle. And wait a second, I'd like to see what would I want to show you again. So maybe we can discuss non-ideal fluid next. So when we discussed the Bernoulli's principle, it was about ideal fluids which has no inner friction. And if there is no inner friction, then the speed distribution is uniform, which means the velocity of any part of liquid in any part of tube is the same. And the velocity distribution looks like the one shown in figure A here. Another example of uniform velocity distribution and non-uniform is shown on figure C. But for real liquids, the velocity is distributed in some other way. So the velocity is higher at the center of the tube and lower at the walls and in the area which is directly connected to the wall, directly just next to the wall. In this area, the velocity goes to zero because in the layer which is in contact with the wall, the speed of particles should be equal, and the speed of particles in the wall is equal zero. So real velocity distribution looks mostly like this. Actually, this schematic picture shows us the triangular distribution, which is not correct. So for cylindrical tube, which is known, which can be calculated, that the distribution has parabolic form. So the maximal in the center of the tube at the axis and decreases to zero at the edges of the tube. Now let's just discuss how we can describe this force of inner friction. For definition of the viscosity, we will consider the simple model in which we have two plates. One plate remains unmoving, so it remains stable on some fixed surface, and another plate is moving with velocity u here. So between the plates, we assume we have a liquid, and we assume that the conditions are those that liquid's velocity distribution is linear. So it linearly changes from zero at the bottom to highest velocity u on the top. Well, then we can describe this liquid behavior as a moving of different liquid layers, one according to another. So we can say that, for example, this layer moves relative to the layer below with some speed, which is difference of speed at this point and that point. So we can define the force of interaction between these two layers. And let us see what so because of viscosity, the liquid tends to stick to the surface of plate, and again here which is says that for laminar flow the velocity of liquid varies linearly, so we can define now this force. Now this force of interaction between two layers should be proportional to the area of the layers. So this is area in the direction perpendicular to the plane of the picture, so it is the area of plates, the top and bottom. And per unit of area, we have some unit of force. So the force is proportional to area. So we will discuss the force divided by this area, because we don't want to get an equation for some specific object. We'd like to get general equation. That's why we should divide by area which can be different from one object to another. And on the other hand, this force is to be proportional to the gradient of force. The gradient is changes of velocity. I'm sorry, it is to be proportional to the gradient of velocity. So it is change of velocity divided by change of coordinate of y. In other words, this gradient of velocity is called rate of strain. Wait a second, let us and so we can say that force per unit of area is proportional to the rate of strain. And the coefficient of proportionality between these two quantities is called viscosity of liquid. It depends only on the properties of liquid. It does not depend on the geometry of experiments. So we can have big plates, small plates, large widths of liquid, small widths. Every time this coefficient is defined only by the properties of liquid. For example, these coefficients have some value for water, another value for oil, or for salt solution. And this is important from the point of view of medicine, because the blood is viscous liquid and it flows through the vessels with big volumes, and the blood flow is a very important process, and we should understand some things related to the blood flow. That's why it is necessary sometimes to measure the viscosity of blood. It is one of the parameters that is analyzed during medical tests of blood. So we'd like to know how to measure viscosity of any liquid. Let us see. For this reason, we can use the so-called Ostwald's viscometer, which is based on the Poiseuille's solution for flow rate of viscous liquid inside a cylindrical tube. So Posel have solved the problem of how much liquids will pass through the cross-section in a given time. If we know the radius of the tube, we know the viscosity of liquid, and we know the pressure difference, P1 and P2. So first, he have shown that the distribution of velocities inside the tube has the parabolic form. Again, here on the picture, it is a triangular form, which is not correct. So correct form would be parabolic. And it goes from the solution of equations of motion for liquids, which is parabolic distribution. Once we know the distribution, we can calculate the total flow rate Q. Now it is not just V multiplied by cross-section, because for different cross-sections, for different parts of cross-sections, we have different values of velocity. That's why we need to integrate over the radius of the cylinder, and for smaller radius we have larger velocity. So velocity changes with radius, but we can integrate it. It is some simple procedure for those who knows the mathematical analysis. And now we can obtain the total flow rate Q, and it is given by Poiseuille's formula. And this formula is represented here. It is equation 16. One can see that flow rate is proportional to R to power 4. It is important part of this formula that we could expect that the flow rate will be proportional to the cross-section area. So it means the R to power 2, PR squared is the cross-section of cylindrical tube. But actually we have PR to power 4 instead. Why it so it is because the larger R, the larger velocity at the center of the tube. At the edges of the tube, we always have zero velocity, but the larger R, the farther from the edges we are, and that's why the larger speed is. And increasing speed gives us two more powers to the power of R. So we have R to power 2 due to cross-section, and R to power 2 due to increase in speed with increase of tube diameter. So we can see that for viscous fluid, flow rate is proportional to fourth degree of radius. Another things here, delta P is changes of pressures. So in contrast to the Bernoulli's law, here we have direct proportionality between Q and delta P. Another factor here is L in denominator. It is because the longer tube, the larger its resistance to the flow rate. So the larger resistance, the smaller flow rate. And factors and one more important quantity is viscosity of liquid. It is in denominator, so the larger viscosity, the smaller flow rate. And you see that, for example, if we discuss blood, if the viscosity increased for some reason, for example, if a person has a a massive loss of liquid, and the blood becomes thick, so the liquid is lost, the blood cells remains in the blood vessels, and blood becomes very thick. The flow rate should remain the same because the amount of oxygen for the brain remains the same. That means the increase in viscosity should increase to delta P. So the pressure should increase, and this pressure produced by our heart. So the increase in viscosity gives increase to the fuse for our heart. So the heart should do larger work. Well, and another term again is radius of vessels. If for some reason the vessels are constructed, then radius decreases, and we have a very strong decrease in flow rate. For example, decrease of radius of vessel by factor 2 gives decrease of Q by factor 16. And that means, again, to compensate, we need to increase pressure. And that's why the radius of vessels can strongly affect on blood pressure and the volume per given time, which is actually Q. So this equation is important from the point of view of understanding the behavior of blood in vessels. Another important application of this equation is ability to measure viscosity by this equation, because all other quantities can be measured. We can measure delta P, we can measure L, we can measure R and Q. So if we measured all of them, we are able to calculate theta. It is almost direct measurement, or I can say it is direct measurement of viscosity eta. Now let us see how it works. So here is again a discussion of equation 16. I will omit it. You can read it yourself. And here is the construction of viscosity, viscometer. So the device for measurement of viscosity. This so-called Ostwald's type of viscometer. It is based on a capillary, a very thin tube, which is located in this part. If we pump this liquid into this part of the viscometer, actually, usually we need to pump some more liquid, so the liquid appears here, and then let it flow down by the force of gravity, and measure time of from its going from this point to that point. We are able to calculate viscosity, but in reality it is not easy to directly calculate the time or viscosity from the time, because during the flow of liquid, its level changes, and that's why the pressure changes, because pressure, according to the laws of liquid dynamics, is equal to rho gh here. So since h changes, the pressure changes, and that's why we cannot directly apply the Poiseuille's law for all the moments. That's why this viscometer is based on comparison of two liquids. If we know viscosity of one liquid, we can find the time of its flow from this point to that point and compare this time with the time for another liquid. Then by a ratio of forces of, well, let us see, what will be different in this formula for different liquids. Radius of capillary is the same, length of capillary is the same, so the only two factors are different. It is delta P and eta. And Q remains the same because volume is the same. So we can say that eta is proportional to delta P. I'm sorry, Q doesn't remain the same because total volume is the same, but Q is total volume divided by time. So Q is different, delta P is different, and eta is different for different liquids. But Q can be easily calculated by volume divided by time. Time is different, volume is the same. So we can say that eta is proportional to time and inversely proportional to delta P. On the other hand, delta P is proportional to density of liquid. So we can find eta if we know density and time. And this is done in one of exercises in our laboratories. In the Laboratory of Molecular Physics, one of the exercises is devoted to the measurement of viscosity using Ostwald's viscometer. Another way to measure is ball falling method or falling spheres method. It is based on Stokes equation for the force acting on the spherical ball. So this force is given by equation 17. If the ball moves inside a viscous liquid, then there is a force of viscosity which tends to stop the ball. This force can be found by equation 6 for spherical object. And one can see this force is proportional to the radius of the ball, to its velocity, and to viscosity of liquid. Radius and velocity can be directly measured. Force can be calculated because we know other forces acting on the ball, which is force of gravity and Young's force, Archimedes force. So we know F, R, and V. That's why we are able to calculate eta from the measurements. It is another way to measure the viscosity, and the equation for resulting velocity is this one. You can see it is easy to find eta from this equation. We have the same, almost the same, but we should change the places of eta and Vs. Well, it is another exercise in our laboratory. What do we have in experiments in medical laboratories? Actually, in medical laboratories, you will not use Ostwald's viscometer or Stokes viscometer because they are not easy for application. One should pump liquids in one of them, put some balls and liquid in another one. So there are some simpler construction which is based on the viscosity acting on the rotation disk inside liquid, and if the force acting on the disk is calibrated, from this force one can easily calculate viscosity. What is done in the viscometers in medical investigations. Well, now, what is the next? Second. Newtonian and non-Newtonian fluids. So we have discussed viscous fluids, and they are those fluids for which the force is directly proportional to rate of strain. But it is not always takes place. Sometimes this relation is not valid. In the other words, one can say that eta is not constant. It depends on rate of strain. And those liquids for which it is true, for which viscosity is not constant, are called non-Newtonian liquids. And blood is one of examples of these liquids. So the blood is strongly non-Newtonian, and increase of shear stress increases its viscosity, decreases its viscosity. It becomes more fluid than it was. And here is some theory for a suspension of solid cells. It says that viscosity should increase with the factor of volume occupied by spheres by formula 19. So if this volume equals to, for example, if the part equals to 1/2, then viscous becomes 3 times more, the liquid becomes 3 times more viscous than it was without spheres. But for the blood plasma, for the blood, this equation is not valid because red blood cells, which are the basic part of our blood, are not a solid spheres. They have big concave shape, but what is more important, they are not solid. They can change their shape in strong way that allows them to pass through the vessels which are smaller than their diameter. And if normally the blood contains about 50% by volume of oh, I'm sorry. It is not about blood, it is about some sort of suspension of small rigid spheres. It is said here that if those spheres occupied 50% of volume, then the liquid becomes a solid which will be unable to flow. But blood remains fluid even if the volume part of red blood cells is about 90%. It is because the cells are very elastic. They permit tremendous deformation and that allows them to flow through the small vessels, as I told you before. So this is a microphotograph, I think, electron microphotograph with false colors of blood cells inside a blood vessel, and one can see that vessel is very narrow, which is smaller than the diameter of one red blood cell, but they have changed their shape. That's why they are able to cross this small capillary. Now let me show you some video about the blood. Sorry, this is not what I'm looking for. So again, for a video for 4 minutes.
If you lined up all the blood vessels in your body, they'd be 95,000 kilometers long. And every day, they carry the equivalent of over 7,500 liters of blood. Though that's actually the same 4 or 5 liters recycled over and over, delivering oxygen and precious nutrients like glucose and amino acids to the body's tissues. All that blood exerts a force on the muscular walls of the blood vessels. That force is called blood pressure, and it rises and falls with the phases of the heartbeat. It's highest during systole, when the heart contracts to force blood through the arteries. This is your systolic blood pressure. When the heart is at rest between beats, blood pressure falls to its lowest value, the diastolic pressure. A typical healthy individual produces a systolic pressure between 90 and 120 millimeters of mercury, and diastolic pressure between 60 and 80. Taken together, a normal reading is a bit less than 120/80. The blood traverses the landscape of the body through the pipes of the circulatory system. In any plumbing system, several things can increase the force on the walls of the pipes: the properties of the fluid, extra fluid, or narrower pipes. So if the blood thickens, a higher pressure is needed to push it, so the heart will pump harder. A high salt diet will lead to a similar result. The salt promotes water retention, and the extra fluid increases the blood volume and blood pressure. And stress, like the fight or flight response, releases hormones like epinephrine and norepinephrine that constrict key vessels, increasing the resistance to flow and raising the pressure upstream. Blood vessels can usually handle these fluctuations easily. Elastic fibers embedded in their walls make them resilient. But if your blood pressure regularly rises above about 140/90, what we call hypertension, and stays there, it can cause serious problems. That's because the extra strain on the arterial wall can produce small tears. When the injured tissue swells up, substances that respond to the inflammation, like white blood cells, collect around the tears. Fat and cholesterol floating in the blood latch on too, eventually building up to form a plaque that stiffens and thickens the inner arterial wall. This condition is called atherosclerosis, and it can have dangerous consequences. If the plaque ruptures, a blood clot forms on top of the tear, clogging the already narrowed pipe. If the clot is big enough, it can completely block the flow of oxygen and nutrients to cells downstream. In vessels that feed the heart, that will cause a heart attack when oxygen-deprived cardiac muscle cells start to die. If the clot cuts off blood flow to the brain, it causes a stroke. Dangerously clogged blood vessels can be widened by a procedure called an angioplasty. There, doctors thread a wire through the vessel to the obstructed site, and then pass a deflated balloon catheter over the wire. When the balloon is inflated, it forces the passageway open again. Sometimes a rigid tube called a stent is placed in the vessel to help hold it open, letting the blood flow freely to replenish the oxygen-starved cells downstream. Staying flexible under pressure is a tough job for arteries. The fluid they pump is composed of substances that can get sticky and clog them. And your typical healthy heart beats about 70 times a minute, and at least 2.5 billion times during an average lifetime. That may sound like an insurmountable amount of pressure, but don't worry. Your arteries are well suited for the challenge.
Just stop it. Well, I have
A constellation of common and treatable conditions could be part of an often overlooked hematological condition called
I'd like to show you 2 more videos, and before we do this, I'd like to tell a few words about laminar and turbulent flow. So we have discussed two types of flow, viscous and non-viscous, ideal liquid with non-viscosity and positive flow for viscous flow. So both those discussion were dealing with so-called laminar flow. In laminar flow, we can uh, consider all the layers of the fluid to remain parallel, and we can divide the fluid flow in parallel layers with no disruption between them. And this takes place at low velocities. If the velocity is not very high, then the fluid tends to flow without lateral mixing. And if in this case, the magnitude of drag force is linearly proportional to relative speed of the object and fluid. In case if the speed increases, then we have strong increase in mixing of layers. So the layer become mixing and the flow becomes unstable. This sort of flow is called turbulent, and there are many examples of this turbulent flow. For example, here is a picture of velocity of speed of a gas, which is stimulation and well, what would you like to tell, Nasser? I see you have raised your hand. What would you like to tell me? Could you tell me? Maybe I don't hear you. Wait a second. Could you write it in chat? If you need to tell me something, please write it in the chat. I remember that we have only 15 minutes to the end of the lecture. So these are examples of turbulent flow. In most cases, we are unable to see these wonderful pictures because the gases and liquids are transparent and we cannot see the difference of velocities. For example, we can see the turbulence on the surface of sea when the wind is strong. But in case of turbulence inside the tube, we are unable to see anything. On the other hand, we can know about the turbulence by a strong increase of drag forces acting on the object, by appearance of sound. In many cases, the appearance of turbulence is related to appearance of sound. And this is used in some medical application, in some simple device, which is used for measuring of blood pressure. Well, here are a few words. How can we theoretically find if the flow is laminar or turbulent? For this reason, there is a dimensionless parameter. It is called Reynolds number, which is the ratio of rho VL by eta. L is some characteristic length of objects. For example, if we consider a ball falling inside liquid, L equals to the radius of the ball. If we consider a flow of a liquid inside tube, then L is radius of tube. In other cases, L can be something else, but in every problem, we can define some length, some characteristic length, and we can calculate this Reynolds number. And by this Reynolds number, we can estimate if the flow will be turbulent or laminar. There is a critical Reynolds number for every sort of problem, for every geometry of problem. And if a Reynolds number of some sort of flow is larger than critical, then the flow becomes turbulent. And critical numbers are very different. For example, if we discuss a spherical ball moving in a fluid, then critical number is about 10. If we discuss a flow in cylindrical tube, the critical number is about 2000. So they are different, but for every sort of problem, there is a value of critical number. If we overcome, if we exceed this critical number, we have turbulent flow. And this can be achieved by changing velocity or by changing characteristic length L. So sometimes, for example, if we discuss the flow of blood inside blood vessel, the turbulent flow can appear if we construct the vessel to make the blood stop. And if the vessel is constructed and its diastolic phase of heartbeat and is opened in systolic phase, then the flow becomes turbulent and it can be heard with a phonoendoscope. And this is used in blood pressure measurements. Let me show you these two short videos. After that, we'll finish our lecture. So first one is blood pressure measurement.
Sphygmomanometer, or blood pressure cuff, is a device that measures blood pressure in millimeters of mercury. It consists of a rubber cuff attached to a pressure gauge. The cuff is placed around the arm, and a stethoscope is placed against the brachial artery. When inflated, the cuff creates enough pressure to block the flow of blood through the artery, which results in no pulse sounds being heard through the stethoscope. The cuff is then slowly deflated. The systolic pressure is assessed when the first pulse sounds are heard. The diastolic pressure is assessed when the pulse can no longer be heard, usually at the point of maximum deflation. Blood pressure is read as the ratio of systolic pressure to diastolic. A reading of 126/90, therefore, indicates that the systolic pressure is 120 millimeters of mercury and that the diastolic pressure is 90 millimeters of mercury.
Now let us see the second one. It is the video with Korotkov's
Hi,
sound.
I'm Josh Farquharson, and welcome to Blood Pressure Audio-Visual Coordination Skills. There are several steps involved in taking a blood pressure measurement, and each step must be completed with accuracy. This is especially true when viewing the blood pressure dial and listening with the stethoscope. You must be able to effectively coordinate what you're hearing with what you're seeing. Just imagine if you recorded a patient's blood pressure as normal when in actuality their pressure was extremely high and they were at risk for having a stroke. Your inaccuracy can have dire consequences on the patient's overall health. This lesson will help you achieve accuracy when taking blood pressure measurements. By the end of this lesson, you will identify and interpret the graduation markings on an aneroid sphygmomanometer dial, and determine the systolic and diastolic blood pressure by reading the dial and listening to the Korotkov sounds. If you ever had your blood pressure taken, you likely noticed that the results were stated as one number over the other number, such as 120/80. The number on top, in this case 120, represents systolic pressure, and the bottom number, in this case 80, represents the diastolic pressure. Let's take a close look at the dial used for determining such a measurement. This is the aneroid sphygmomanometer dial, also known as the blood pressure dial. The dial has the letters mmHg because blood pressure is measured in millimeters of mercury. Also on the dial, you'll notice that there are lines in various sizes. The largest lines represent values.
Well, so you have listened those Korotkov sound, and let me remind you that they appears due to turbulence. So when the blood vessel is completely blocked by the inflated cuff, the flow becomes turbulent. When it opens again, the flow becomes turbulent, and this leads to appearance of some specific sound, which is called Korotkov sound. You were able to hear that there are 5 different types of this Korotkov sound. If you look to this video once again, you will be able to hear it more accurately. And so this is the description of sphygmomanometer. Again, another slide with description. Here are the questions, and we have only 4 minutes to the end of the lecture. So now I'm going to send you the files with my links. Sorry, how to send it? I need to use chat. Oops. I don't see how can I. Oops. I'm sorry. And I'd like to remind you that you should write your name in this chat. Wait a second. Oops. I have stopped the demonstration. Actually, it is not necessary anymore, and I'll stop the recording.